right, today we're doing a lesson on 16.7b, which is a continuation on surface integrals with a topic called flux. Ready for flux?
Nope.
All right. So, first quick, horrible explanation of flux. Flux is a flow. Essentially, it's a flow of a vector field through a surface. That's my limited understanding of flux. So let's read what our old book says, and then we will talk about what Wikipedia says, and then you can come to your own conclusions or do your own research beyond. If S is a surface submerged in a fluid having a continuous velocity field F, then the flux of F across S is the volume of fluid crossing the surface S per unit of time. Okay, so from Wikipedia. So the field lines a vector field F through surfaces with unit normal vector n. The angle from n to F is theta. Flux is a measure of how much the field passes through a given surface. F, that's your field, is decomposed into components perpendicular and parallel to the vector normal to the surface. Only the parallel component contributes to flux because it is the maximum extent of the field passing through the surface at a point. The perpendicular component does not contribute. The top picture shows three field lines through a plane surface, one normal to the surface, one parallel, and one intermediate. The bottom picture shows a field line through a curved surface, showing the setup of the unit normal and the surface element to calculate flux. So there you go. Basically, if I understand flux right, it's a measure of something flowing through something else. There you go. All right. Something going through something else. Flux. All right. Okay. So let's move into how to calculate flux. So just so you know, when we did line integrals, the first day we did line integrals, like traditional line integrals, which were integrals with respect to arc length. And then afterwards, we learned how to calculate line integrals of a vector field, which allowed us to do line integrals of these dot products. And so you had your f dot dr, and it was a slightly easier way to calculate the line integral, but it was a different context, right? So we had line integrals with respect to arc length, and then we had the work, which was a line integral of a vector field, and you had your f dot d, or a particle traveling through a vector field. So yesterday we did surface integrals, which was basically with respect to surface area. So those are like traditional surface integrals. Today we're going to do surface integrals, again, involving vector fields. So it's kind of like we did line integrals traditional, line integrals vector fields. Yesterday we did surface integrals traditional. Today we're doing surface integrals with vector fields. Okay. So a surface integral through a vector field is actually called a flux integral. So either way. All right, so if big F is your vector field and all of its components have continuous first partial derivatives on the surface S oriented by a unit vector n. I should note that our book from last year used a capital letter N, and our book this year uses a lowercase n. Don't let that throw you off, okay? N just means the vector normal to the surface. All right. The flux integral of F across S is given by the surface integral of F dot n, the dot product of F and n. If you multiply in the density of the fluid, then if the vector field represents fluid, then the integral represents the mass of the fluid flowing across S per unit of time. So there you go.
So the normal vector n is the y component?
No, I'm going to show you how to compute normal vector in just a moment.
Are they two n's represented?
Oh, two different things. Good question. You know, that is why we really shouldn't use an uppercase n. So, yeah, let's call this a lowercase so you don't confuse it with that guy, because totally different things. Thank you. Yeah. Completely different things. That's a vector normal to the surface, and that's just a component of the vector field. All right. So, sorry. N has an orientation. So your vector normal to the surface, if you have a surface, there's technically, if it's just a surface, not a solid, but just a surface, then technically, if you have a point on the surface, there's two normal vectors, right? There's one going this way and one going that way. So how do we know which N we're talking about? So they have to tell you, is the N oriented depending on your surface? It could be N's oriented up, N's oriented down, N's oriented out, N's oriented in. There's an orientation for N, and that's what we're going to talk about in here with the computation. It depends on the orientation of N. All right. So how do we evaluate a flux integral? So if z equals g of x, y represents the surface S, and again, we will see problems over the next few days where the surfaces are sideways, and so you have to be able to interchange your x's, your y's, and your z's depending on which way the surface is facing. But if z equals g of x, y represents surface S, and r is the projection of z onto the xy plane, then if the normal vector n, and I'm going to call it lower n now just so that we don't get it confused. Okay, if the normal vector n is oriented up, so when you have a vector, the normal vector oriented up, then you end up with this normal vector n being, so it's kind of like, it's a little bit like the gradient, like you do partial x, partial y, and then a 1. Except you make the partial x negative and the partial y negative, and then your z component is just a positive 1. And so and then if the vector is oriented down, then it's positive partial x, positive partial y, negative 1. And the way that I remember these is if my normal vector is oriented up, then I know that my kth component would be positive. This go up. So that's how I think of it, as positive up, negative down. So I look at my k and I think, all right, I'm going up, k is going to be positive, make all the rest negative. If I'm going down, k is going to be negative, make all the rest positive. It's kind of weird. Oh, I thought you were only leaving like 10 minutes early. You're leaving now. Oh, okay. Good luck. Hope it goes well.
Could you explain one more time why the other two components are negative?
We could research a little more why. I think your new book actually explains it a little bit better. So I'm going to pause recording for a moment. All right. Notice that these integrals, though, what's nice about them is you don't have to integrate over the arc length anymore. You're integrating over the area of the region, which we were doing before. We're doing it integrating over the area of the projection onto the plane. So anyway, but you don't have to worry about the square roots of stuff squared, which is kind of nice. All right, so we're going to go ahead and try an example. So, yeah, doesn't it look good? It makes me think of when women put those caps on their heads and pull the hair through to dye it. Is that, you know? Okay. So anyway, And I don't know if you guys know what that looks like, but anyway, let S be a portion of the paraboloid z equals 4 minus x squared minus y squared, lying above the xy plane, oriented by an upward unit normal vector. A fluid of constant density rho is flowing through the surface S according to the vector field big F of xy, bless you, big F of xyz equals xyz. Find the rate of mass flow, or in other words, the flux through S. All right, so we're doing a flux integral. So we have, it's the integral, if we set it up, it's the integral of f dot n. Yeah, I don't want to give you guys too much. All right, so let's go ahead and just figure out first. So our f is x, y, z, but our z is 4 minus x squared minus y squared. So we can rewrite f of x, y, z as x, y, 4 minus x squared minus y squared. And then your n, your normal vector part, would be the vector of, so it would be negative partial x, negative partial y, and then positive 1, because our normal vector is oriented up. So figure out your vector n, negative partial x, negative partial y, positive 1. Yes, please.
So is the orientation always given to us in the problem?
Yes.
Oh, sure. Take all the tissues you need.
Now, I wrote this first with respect to x and y. So this right here, this circle, right, that's the projection of, that's a projection of your surface onto the xy plane. So you can find that by just setting z equal to 0 and think about what your equation is, right? You get x squared plus y squared equals 4. Right? So remember that we're integrating over the area of this region. So you're integrating over the area of your projection onto the xy plane. So see, this is what's going to determine the limits of your integral. So something to something for y, something to something, something to something for x. So see if you can figure out your integral limits in terms of x and y, your integrand in terms of x and y, and then we'll take a look and see if maybe converting to cylindrical might be, or polar might be easier. There's a lot of problems in the next couple sections where we'll be converting to polar, and a couple where we convert to spherical. All right, so just to make sure that we're on the same page with the original setup. So this is your F, right? So this is your big F written in terms of just X and Y, right? So you pull the Z out, replace it with what Z is. Everyone understand how to rewrite F? Yes. Okay. That's your N. That's partial x, it's technically negative partial x. We get a negative, so negative makes it positive, right? Negative partial y, positive 1. Then we want to integrate over this circle. So if you solve it for y, then you're going y goes from negative root 4 minus x squared to positive root 4 minus x squared, and x goes from negative 2 to 2. All right, before we do anything else, I would go ahead and do the dot product and just see what you get. Is that okay? Oh, okay, you went. Yes.
Can we do it in polar?
That's what we're going to do. Yeah. So first, but I would do dot product first. So I haven't tried this like inverted to polar first. I only know how to do it with x's and y's for setup and then switch once you've got it like good to go. So, all right. So once you've cleaned up your dot product, you should get x squared plus y squared plus 4. Is that what you got? Yes. Oh, good check. Oh.
Like, why does it include that?
Row, you could stick a row in. You know what? I didn't even put the row in. You're right. I should stick the row in. But consider row for when it represents density just be a constant. It's okay. It's not like the variable row in spherical coordinates. It's two different representations based on row.
So like if they gave us the numerical value for the row,
You would just put it up front. It could just be a constant multiplier. But thank you for pointing that out.
if they don't
Hi.
remember who, just put row.
Just put row. Yeah. So here, let's do this. Row, 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 row. Okay. Tajesh, did you need something? Or were you just waving? Oh, okay. All right, good. All right, so now let's take this and convert this to polar coordinates. So it's not too hard. What does x squared plus y squared equal? R squared, right? And then so you do times r dr d theta. Your radius of your circle is going from what to what? 0 to 2, and your thetas would be 0 to 2 pi. Yes, Dursa.
Okay.
Yeah, you can convert to polar first. And still
Can you, and it still works?
Yeah.
Okay. It makes me nervous.
Your pre-dot product polar and then do the dot product.
Is that actually easier or harder? Because that looks really
I think it's
complicated. Yeah.
I think it's
Because
similar.
you'd end up with all like an r cosine theta and an r sine theta and a 4 minus r
You end up
squared.
with 2r squared cosine squared plus 2r squared sine squared plus 4 minus r squared, which like adds up all times r, which adds up to r cubed plus 4r.
Okay, so you get it.
It's similar.
It's similar.
I don't think it's like a ton harder. I don't think
Okay.
it's easier.
Yeah.
If you can, did you have to still add the extra r?
Yes.
Yeah, you still have to multiply.
Yeah, you still have to multiply by r. Okay, good. So go ahead now and evaluate this integral. I am pretty darn sure. I was taking a close look at your big quiz for this chapter today, and your test for this chapter, which I'm still kind of working on and writing, but I'm pretty sure it's all going to be no calculator. So might as well kind of get ready to start evaluating some integrals. I might do a couple where you just set it up. Write the setup, but do not evaluate. Yes?
So for that x and y coordinates, can you, like what I did when I set it up, is I just did like 0 to 2 and 0 to the other thing and then multiplied by 2. And that worked for.
If it's truly all symmetric, it has to be all symmetric. Yes. So, guys, what Lily was saying was, could you just take this double integral from 0 to 2 and 0 to root 4 minus x squared, right? And then times 4. And yeah, you could, because it's totally symmetric about the z-axis. It would be okay. I think it would be fine.
So you do times 4 or times 2?
Well, you'd have, this would be one doubling, and then if you did another 0, that'd be another doubling. It would be times 4. Yes?
So like, do you include the row in your final answer?
Yes, I totally ignored it for this whole problem though, but I will add it in. Yes. Okay. So, row. All right, so I got 24 pi row. That's crazy. I totally ignored the row. I didn't even think about it that they said, hey, row is the density. If you're given a density function, you just multiply the density in.
So can you just?
But if row is representing a constant, then you can just put it out front. And in this case, row, there was no function given, so it just represents. It just represents constant. Okay. All right. So main gist of surface integrals through a vector field. Write your f in terms of x's and y's. This is just like yesterday. Then you're doing the dot product of f and your normal vector, which is negative partial x, negative partial y, 1, unless it's oriented down, then it's the opposite. And then you're integrating over the area of the projection onto that xy plane. It's really the whatever two variables it's given. All right, let's try another one, unless there are questions. All right, so find the flux of f through s. If f is the vector xy0 and s is the surface in the first octant with the equation 2x plus 3y plus z equals 6, where n is the upward unit normal vector to s. All right, so see if you can set up your flux integral based on this. Pause it. All right, so solve, quiet down please, solve for z. So your, quiet down. Okay, f is xy0. The nice thing is 0 is 0. You don't have any z's that you have to replace, right? So you just stay with xy0. Then this is if you solve for z, then negative partial x is 2, negative partial y is 3, and then your z component is 1. And then how do you find your limits for your integral? So when you if you set z equal to 0, you get, so 3y equals 6 minus 2x. So y equals 2 minus 2/3 x. Okay, so if we were to sketch the region bounded by this graph, and then the two axes, right, that triangle would be what we're integrating over. So I would go dy dx, where y is going from 0 to this line right here, and x is going from 0 to whatever that x value is, which if you set y equals to 0, you get x equals 3. So you're going from 0 to 3. All right. So doing the dot product, you end up with an integrand of 2x plus 3y. Integrate with respect to y. You get this lovely, this is me, I didn't multiply, I don't know why I didn't multiply it out, but I didn't multiply it out. So anyway, so plug that in for y, and you get this beautiful integrand. I would distribute this guy so that you don't have to worry about the product, but this guy you could just integrate as is, dividing by the slope. So, here, wait, let me extend. Okay, so think of this 2/3 of 6. You get 4x, so the antiderivative would be 2x squared. Here you get negative 4/3 x squared, so that the antiderivative would be negative 4/9 x cubed. Here you have 1/6 times 1/3 this cubed divided by negative 2. So it all works out to be negative 136 times that quantity cubed from 0 to 3. And the mistake that I saw, the only mistake I saw, was be careful that you don't assume when you're plugging in a 0 that everything is 0. Because if you plug a 0 into this term, there's still numbers, right? So just watch out. Don't assume 0 when you plug in a 0. So, and you end up with a total of 12. Any questions? Okay, they're not bad, right? Okay, so flux integral, that's all we got. So, flux integral, just the regular surface integral of f dot n. Just got to know how to find n. All right, so now what I'd like to do, I'm going to pause. Okay, so this is number 1 from tonight's homework. Evaluate the surface integral f dot ds for the given vector field f and the oriented surface S. In other words, find the flux of F across S. For closed surfaces, use the positive or outward orientation. Note S is the parallelogram of this exercise with upward orientation. So I'm going to have to go back to the homework, and so I can click on the link and find the parallelogram they're talking about, right? But yeah, I'm going to have to first before I can do anything, because I can't even replace the X's or Y's or Z's or whatever needs to be replaced without knowing what S is. So I'm going to escape out of here, go back to the homework. Whoa. All right, so are they trying to like get a 2-for-1 in this problem here? Let's see. Goodbye. Minimize. Oh, okay. So they're given the parallelogram parametrically. So you could still. I don't know if we want to convert or not. So if our R of U, V is U plus V, U minus V, and 1 plus 2U plus V. And U is going 0 to 2, and V is going 0 to 1. So you find your R sub U. So you just get 1, 1, 2. And you find your R sub V. And you get 1, negative 1, 1. Whoops, that's an R. Okay. All right, then your R sub U cross R sub V, which is like your N, is going to equal 1, 1, 2, 1, negative 1, 1. So I get 1 plus 2 is 3. 1 minus 2 is negative 1, so it's 1. Negative 1 minus 1 is negative 2. All right, so surface integral. So the surface integral would be your F. So you'd have to write F, quiet please, gentlemen. You'd have to write F in terms of U and V. So you would have the vector U plus, you'd have, yeah, it's really just U plus V plus U minus V plus 1 plus 2U plus V. That whole thing, that's weird. Okay. So, oh, here we go. This is your big F. Yeah, I was going to say, this isn't vector form. All right, so this is your big F. So our big F in terms of U and V, if we want to do the whole thing in U and V, if I do this right, would be 1 plus 2U plus...
Guys, don't do it. Do this cross product first, and then it cancels. The first two terms cancel, and then you can just plug it in. That's easier.
Really?
Yeah.
That's my cross product.
Yes, if you do the cross product.
Oh, the dot product. Oh, okay. All right. I can do the dot product in terms of x's, y's, and z's and then convert at the end?
Yeah, because that would be 3z.
Oh, okay.
Minus 3z. So
Okay.
they cancel.
All right. Let's do it. So F dot N So we have z e to the xy, comma, negative 3z e to the xy, comma, xy dot 3, 1, negative 2. 3, 1, negative 2 equals 3z e to the xy minus, xy minus 2xy, and then these are gone, and life is so much easier. Thank you. Okay, so we end up with negative 2xy, so it's just the integral of negative 2xy, d whatever. So now let's rewrite this in terms of u's and v's. So negative 2 times x is u plus v, plus 2, plus 2. Y is u minus v. And then your v's are going from 0 to 1. And your u's are going from 0 to 2. dv, du. So not bad. I mean, we got to do it, but it's not bad. So u squared plus uv minus uv minus, this is u squared minus v squared. Du. I don't know how to get rid of that r. All right. So integrate with respect to v, so get negative 2u squared v plus 2/3 v cubed from 0 to 1. Integral 0 to 2 of, plugging in a 1 for v, so negative 2u squared plus 2/3. All right, minus 0 du. Did I do something wrong? Is this, I'm okay? Okay. All right, so then negative 2/3 u cubed plus 2/3 u, 0 to 2. So negative 16 thirds plus 4 thirds. So I get negative 12 thirds or negative 4.
That's what I got too.
That's wrong?
Wrong.
Yeah, that's what I got too.
It's positive 4.
Is it positive 4? No, I'm trying to think. No, that wouldn't be it. I wonder if it's because something to do with like the negative, negative, positive for your normal.
Isn't it going upwards? So it has to be positive, negative, so it'd be negative 3, negative 1, 2. Is that not how it goes?
But I don't know if that's the same parametrically. Let's see. Let's see if they tell us anything else. Flux, unit sphere. They don't do anything to change it. Oh, look. So, no, that's just relating it. All right, I don't know. I will have to do more research on flux over parametrically defined surface, but it looks like we got the right answer, just negative, and it should be positive. So, I'm going to go with that.